good, Bob? Okay. So, you all know me. I'm still Drake. And for some arcane reason, I decided to do my senior project on the evolution of chairs. Mostly because I just want to build a chair. And I/the advisors figured, well, it wouldn't be a bad idea to research the last 200 years of it. So, that's what's led me to this. It's where I am right now. Lecturing you guys for the next half an hour about something none of you care about, but all of you use. So yeah. And before I actually even make sense, this will include instruction on history, geometry, and design ideology. I'm not in any way responsible for the education that may follow. Pay attention at your own risk. I'm going to start with Michael Thonet's number 14 chair. It's the starting point of the last 200 years of development for multiple reasons. It featured either the first or some of the first examples of steam bending wood, which is done by putting beech wood in a sort of kiln, and you pressurize it with steam, after which it is soft enough to form by hand, and you can form it into those curves without it breaking. It also featured contoured seatings 150 years before it was cool. And it also, most importantly, encouraged mass production in an age of small-scale artisans. So, and compared to something that you would hand carve out a solid chunk of wood, this is unimaginably cheap and efficient. Frank Lloyd Wright's chair is an example of people outside of the furniture field designing economical, revolutionary, and attractive chairs. This chair is cost-effective to manufacture as a result of its design. It also features some significant experimentation for its time, with its incredibly square design. The BA armchair is an excellent example of the end of the streamlining design era and the beginning of the contemporary design era. It features sweeping curves, but in an economical and way that conforms to the user. It also featured enameled/powder-coated finishing, which is one of the first examples of the furniture industry starting to use plastic. Before the 50s, it basically was non-existent. Benton-formed aluminum, while present beforehand, in addition to steel, really became the feature of chairs around the time of this BA chair. Likely due to the low cost strength it provided and the fact that there was a lot of aluminum left over after World War II. The Boloom chair is endemic of the pop art era that it's surfaced in, highly reflective of its subject while having an identity of its own. It also displayed the start of the minimalist movement, in that it was just formed wood with minimal upholstery. The ergonomics of the chair are excellent in that they feature a form that conforms to the occupant without the upholstery involved. Aeron, the pinnacle of modern chair design. This chair features everything required to work in our modern world. The incredible ergonomics that this chair provides as a result of its suspension seating with posture support means that anyone can adjust and sit in it comfortably for 8 hours straight. The design of this chair helps to accentuate the ergonomics of the chair. How the entire chair is built how the entire chair is built off of its own included superstructure. The Aeron chair is also an example of the pinnacle of the minimalist movement. It has exactly as much material as is required to support its occupant while maintaining comfort and usability. So now that I've talked about what's good about chairs, let's talk about the principles that make those chairs strong. First, we'll start with squares. Squares are bad. I'll just start with that. It's a weak shape, and let me show you why. This is why. When you apply force to any side of the square, it deforms. This is because there's nothing limiting the movement of the sides. Triangles, on the other hand, are great for many reasons. The first among them being that the triangle will not change shape when force is applied. Triangles can only change shape via the application of force when that force is enough to break one of the legs of the triangles. This makes triangles some of the strongest shapes possible. Curves are great, just like triangles, but for an entirely different reason. Curves are strong in a different way from triangles. Curves are strong because they evenly distribute load applied to the top, out, and through the rest of the curve. So in order to get a curve to fail, you must apply enough force to the top of the curve to get the base of the curve to move outwards. This is made difficult by the fact that pressing the curve down will increase the amount of force required to move the base outwards. As a result of this, curves and arches rarely fail. Steel cables are great. They are cheap, relatively easy to make, and are almost as strong as their solid steel counterparts. This lost strength is instead traded for additional flexibility, allowing for ranges of movement that would make solid steel brittle and stiff. Steel cables are not immune to this gradual stiffening and hardening. Unlike solid steel, cables will develop severe internal stress and wear. The combination of these two factors make the lifetime of steel cables significantly shorter than that of solid steel. This still leaves steel cables a better alternative where motion is going to be constantly involved. So remember when I said that squares are bad? I forgot to include a very important detail. Squares can easily be divided into triangles. Simply add a diagonal brace to any square or rectangle, and you have two triangles. Now you cannot shift the square without breaking off one of its sides. Even then, there's still half of the square intact. What is important about this is that with enough tenacity, anything can be constructed out of triangles. Even if it is only an approximation, reconstructing something out of triangles will greatly increase the strength and rigidity of that object. So, warnings. This section may include detailed details of the details of my design process and its details. If this is excessively detailed in an offensive manner, feel free to read the details of the previous disclaimer. So enjoy the gratuitous gray details a little while longer. So, you know how I go on almost completely unrelated tangents? This is what's going on my head when that happens. Let's explore my thoughts. Well, I want to build a chair. What kind of chair do I want to build? I guess I want to build a desk chair. But why would I want to do that? Well, I could do it because it's highly mobile, or because it's more symmetrical than a normal chair, or just because I want a better desk chair. So if I'm building a desk chair, what material do I want to use? Well, I could use wood, because wood is easy to work with, it's well priced and easily available, but I might not want to because it's hard to repair mistakes or damage, and it's inconsistent in density and strength. Well, I could use metal. Metal's pretty easy to work with. It's also really forgiving, and it even has consistent strength and density. However, it is expensive and is kind of a little harder to get. Plastic is great. Plastic is inherently designed to absorb as much energy as possible before breaking, and it's really cheap and readily available. Unfortunately, it's quite costly to manufacture on a small scale. Plastic is, and in addition to that, plastic is fragile and not as inherently rigid as metal. I guess I'll go with metal. This is full. It's even falling more. Excellent. There we go. So, if I'm using metal, what kind of metal do I want to use? Well, I could use steel. It's pretty strong. It's quite hard. And it's also heavy, so I might not want to. I could also use stainless steel, which has much higher corrosion resistance, meaning it doesn't rust. It can be a good bit harder than steel. However, it is a bit more expensive, so maybe not. I could also go with aluminum. It's very light. It can be stronger than steel for a higher price and a lower weight, and it has the downsides of being weaker than steel and softer than steel on most occasions. So maybe not. I guess I'll go with steel. So, now that I have that figured out, what layout do I want to use for the general aesthetic of my chair? Oh, that is out. That is more out. Thank you, Resi. Well, I could go with patterns of 4 or squares. I could go with patterns of 5 or pentagons, or I could go with patterns of 6. Well, squares don't exactly provide enough support. Pentagons are hard to do on a small scale, and hexagons are kind of nice. I do like them. They're really symmetrical, and they are one of the few polygons that can fit into flat arrays. I think I'll go with those. So now that I figured all that out, how am I gonna do specific parts of the chair? Like, how would I drive an Acme screw in the chair to drive the chair up and down? Well, I could use a crank and gear set. I could couple the Acme screw itself to the gear drive shaft, Or I could use a drive shaft with an internal D shaft, which is it allows it to extend out without the internal shaft rotating on the inside, and connect that to the gearbox above the base of the screw. That's really complex though, so I think I'll just leave that alone. Well, are there going to be, do I want to put shocks in the casters? No, it's redundant and expensive. I just shouldn't bother. Is the seat going to be supported? And are there going to be shock absorbers? Apparently yes. How am I going to do that? Well, I could do I could have the adjustment column of this seat, which you can see part of down there. I could have that be a series of plates suspended by springs in between each other, so that the one actually connected to the screw that moves up and down has smooth movement and gives you cushioning when you sit on it, so it absorbs impact. Or I could do a tension system in the legs that pull the legs towards the center of the chair, and split on the opposite, splay the legs outward when weight is applied. Or I could even do one plate kept from touching this plate below it by springs. That's a lot simpler. I think I might go with that. Also, it would look like this. For some reason, I felt like this was necessary. So, I want to use linear bearings to keep the whole array in alignment. So, how do I keep those in place? I could make casings I could make rough casings for those and just weld those into place and put the bearings in. Or I could get ones that are physically mounted to the plates itself via a flange and screws. So, are the armrests for the chair going to be adjustable? How so, if yes? Well, they could be manually adjusted by Acme screws and an adjustment wheel, or they could be automatically controlled via DC motor and gear sets. Although that too is expensive and complicated. Let's just leave that alone. Is the back going to be adjustable? Yes. Well, how could I do that? I could do that by keeping the back rigid and have an angle between it and the seat adjusted from 90 to 135 degrees, so you don't lie back too far. I could also have it be made of an array of hexagons, like that. Or I could have it be made of an array of hexagons that doesn't shift when you sit back into it. But I guess that would be good, but it might be a little annoying to not have an active system, or not have a passive system where you just lie back into it and then it moves with you. I think that might be the best option here. So I'll go with that. So now that I've finished all the basic mechanism specific stuff, how am I going to do the general design for the chair? Well, let's start out with what I want. I want the chair to be as low as possible. I want it to raise high enough for me to sit comfortably in it, and I want the maximum weight to be 400 pounds before any part would fit. I also don't want it to constantly have to readjust it, and I want to have it designed and built in the metric system for simplicity. I initially tried to accomplish that by designing the chair in the metric system, using conversions from imperial to metric to best approximate the dimensions I wanted. However, when I started incorporating the parts from McMaster-Carr, I got frustrated with doing things in metric because the chair base and redesigned the chair base in imperial units. I also originally tried to design the chair using an array of 6 hexagons with casters mounted to the bottom and a square pipe connecting the top of each one to the central adjustment column. I think you can see that there, not sure. I realized that wouldn't work though because the mounting bolts for the casters and the connecting square would overlap. So how could I troubleshoot that? Well, I could change the mounting system so that the square pipe would be mounted from the side of an intermediary piece, kind of exactly like that. And this did lower the overall minimum height of the chair and probably added some more stability. However, it was a bit inelegant and the minimum height of the chair is still too high. So I redesigned the intermediary piece using only the bottom half of it and putting in a vertical mounting plate facing inwards, with a stabilizing angle brace so the square pipe would still be mounted to it. This solved the inelegance problem, but did not reduce the minimum height of the chair enough. I solved that by having the angle be from a 15 degree incline to a 15-degree decline. So, up and down respectively. And that ended up significantly lowering the minimum height of the chair. That's good. So now that that's fixed, I have a new idea. What if I change the side walls of the adjustment column so that the side walls are made of hexagonal arrays? I drew this out and eventually decided that it would be best for symmetry and aesthetic sake, and that it would be best to have a central row of hexagons made of steel, with 2 half rows made of polycarbonate, a strong and clear plastic. Also, considering each row would be comprised of regular hexagons, this means I'd be able to laser etch designs onto the surfaces. Yee. And then I would be able to illuminate the polycarbonate from the edges to make the etched parts glow whatever color of light was being shown into it. Have a glowy steel chair. So, now that I have all of that done, I need external revision. And the most important part about designing my chair was making sure that it would work for the requirements I needed it to fulfill. This included the chair being comfortable, ergonomic, easily adjustable, able to easily bear 400 pounds, and to have as little give as possible. Unfortunately, I did not have enough experience in this area to assess these items beyond a level of no or maybe. Instead, I met with experts at Fox Valley Tech who had experience with working with steel, and an expert at Krieger International who was highly experienced with the design and ergonomics of chairs. These experts could not only tell me what was wrong and what was going to work and why it would work, but how I could improve it and to better accomplish my goals. I really should have taken a drink earlier, so I'm just going to do that now. These revisions were made most in the areas of the chair where I had highly complex, frequently moving parts. As a result of this, I had to completely redesign the height adjustment column and the backrest adjustment mechanism. The adjustment column used to feature about 20 moving parts and was supposed to be driven by a rotating screw that would move a set of 2 plates up and down along a series of linear bearings. Could you please raise your hand if that sounds unnecessarily complex? Yeah, I didn't know that. I couldn't figure that out at the time. At the time, I thought that I could only do it that way. I guess things change. So I wanted an easily adjustable, Acme screw-driven height control mechanism with a spring suspension that wasn't going to change height when I turned the seat. I eventually decided that I only needed 2 of those attributes. With the advice of my live source at KI, I decided that the most important was the Acme screw, and the ease of use of the system were the most important aspects. I redesigned the adjustment column accordingly to the version you have in front of you. It may look familiar. This version, like the last version, is driven by an Acme screw. It's easy to use, and unlike the last version, is driven by rotating the entire assembly, chair and back and all. This bit here is really special. By changing the plates from the center of that column to the outside of the column and bending them around the corner, I have managed to get the strength and rigidity of 12 pieces of steel while only using 6, and using even less steel than I would have otherwise. As a result of this change, I have reduced the cost of the entire chair by half or significantly more, while also making it easier to assemble and use by reducing the number of moving parts and parts in general. Remember that thing I mentioned like 3 minutes ago? The backrest adjustment system? Me neither. I wrote this down to make it seem like I had planned to do this little bit. This abomination here is what I plan to use as the glorified hinge between the back and the actual seat itself. It was meant to safely limit the user's range of motion while also producing a robust support structure for the backrest. If you can't tell, this is overly complex for a number of reasons. First, it uses large, overly detailed parts with a lot of distinct angles. Second is that the axis of rotation of the entire mechanism would not be under the hips where you sit back with, so that wouldn't be comfortable. And third is that it needs a large amount of precision over an area that will not maintain that precision during normal use. If you see that little curved L shape there, That's what I'm talking about. It would use those in conjunction with a pin in the center to provide a heavy-duty hinge that would flex over time, which is not something you want a hinge to do. That's very bad for design. As a result of those three reasons, this mechanism may not work. Well, if at all. You all know what my approach is on solving these problems by this point. Can you guess what I did to fix this?
Consulted some.
Redesigned it.
Yes, I did redesign it, but anything beyond that? Huh? Jared?
Reduce the amount of parts and make do with what you have.
Yes, that is what I did. Good job, Jared. I did this by redesigning the mechanism to have a total of 2 moving parts, instead of having 2 sets of 4 moving parts that were also directly connected to the back and the seat of the chair. Instead, I elected for using 2 pieces of steel tubing and 2 pieces of custom hinge brackets that look remarkably like that. This way, I reduce the amount of pieces I'm using by half and get more stiffness and reliability while not needing high precision. So, let's go to the timeline of this project. Why is this taking so long? But first, let's have a warning. This will get boring. It will get boring fast. Hopefully, you can stand the next 12 minutes of this presentation where I drone on with a few choice memes in the background to tide you over. Also, this may or may not include detailed discussion of my ridiculous process and how it works. Let your doctor know if your productivity increases or decreases by at least 20% tomorrow. That could be a sign of you finally utilizing the resources you have available to you and the peeper eagle to help you with what they can. And it was totally necessary to include those additional transitions. Fight me. I'll start off with this. Probably the least obvious and most important thing in this project was this, my PLP. My PLP was of very little significance to me in 8th grade when I personalized it. I was supposed to personalize it, make it my own, and use it as a guide to reach my goals. Naturally, I covered it in duct tape and drew an engineer on it with one of the spiciest memes of my time on it as well. And you can see the math for that there. So, the year is 2015. I have just finished building my desk after the course of several months. Suddenly, I realized something important. My current desk is far too big for my old chair, and my old chair is on its last legs. I thought to myself, considering I just built a massive desk, building a chair couldn't be all that hard. I started with the first iteration of my design, which you can see now. This design was very basic and was short-lived due to the fact that I had not initially accounted for how I would mount the casters to the bottom of its legs. The second design was a little longer-lived. As you can see, it featured the intermediary pieces in between the caster plates. These pieces made it so I could connect the central column to the wheels while leaving the casters easily accessible. The primary function of these pieces was just to provide a surface to weld a square tube onto, nothing more. The third design was a little more fleshed out than that of the previous designs. With this design, I finally created the finished model of the adjustment column, which may look remarkably familiar to the current model. I implemented what I had thought would do well to keep the mechanism in alignment and help facilitate the springs intended to absorb impacts. This incredibly complex model ended up featuring a lower and an upper plate in the adjustment column that would raise the seat up and down. The Acme screw, the weird screw that I pointed to earlier that has trapezoid-shaped threads instead of triangle, would drive the lower plate up and down, while the top plate, the one actually connected to the chair, would be riding on that on top of springs. So, when you sit on it, the top plate moves down to a limited amount, and when you raise it up, it'll move it up and down by proxy. So, get a nice suspension without having to deal with all the crazy gas piston stuff. The fourth version featured some important design tricks in order to lower the minimum height of the chair and use less materials. The first was accomplished quite simply by flipping the angle of the square tubes that connected the center column to the caster ring from 15 degrees up to 15 degrees down. The second main revision was to change the intermediary pieces from hexagonal prisms to a bridge piece with a triangle on the top to provide the right angle required for the pipe. I also made some aesthetic changes, like with the sides of the column being comprised of hexagons. On August of summer 2016, I took the metal forming fusion class at the Tech. During this class, I got the chance to learn how to use SolidWorks and heavy-duty metal forming machinery. These two new additions to my mental toolkit greatly helped me to redesign my chair in a significantly more economical, robust, and easily manufactured iteration. The helpful expertise I had available to me from Trent Schloss and the other instructors I had there also helped me to employ the principles of KISS. Keep it simple, stupid. The fifth and final version is almost an entirely different beast from its predecessors. It used to just be a conversion of the fourth version into SolidWorks, but now features many parts and design elements unique to itself. My chair no longer features an overly complex adjustment mechanism. It is now to be made from a total of 66 pieces, instead of 56 pieces making up the wheelbase alone. That's everything the casters are attached to. All that stuff on the bottom, not including that column and the seat. That's 56 pieces on its own. This reduction in complexity should reduce the cost to somewhere in the range of 1/5 to 1/10 of the original cost.
Cool.
I assume you can all remember that projects need to be proposed to be started, right? Neither did I. Well, neither do I. I did propose this one, though. I guess it was kind of late, though, considering I did start this project essentially a year before I wrote the rationale. I did need to have a rationale. It was kind of like I did need to have a rationale. It was kind of like an extension of my PLP in that it helped me to create my own extrinsic motivation. I don't think there's any immediately obvious relation, though. My college search was also a sort of motivation, like my PLP and proposal essay. It helped me to put what I wanted on paper and prepare for the next step in my life. I had visited the University of Nevada, Las Vegas, and the University of Nevada, Reno during spring break of last year. I really enjoyed the experience and had determined that UNLV was exactly what it sounded like. Las Vegas College. One more is there. And I learned that UNR would be an excellent choice for me. 2 months ago, I learned that UNR would charge me an additional $7,000 per year in tuition, since I no longer live in the state. As a result, I applied to and have been accepted to UW Fox and UW Platteville, which I will be attending in that order.
Wow.
I met with my live sources from KI on January 17th. On that day, I got to take a tour of KI's Research and Development Office and see the specifications that they test their chairs to. I also got to learn what some of the crucial golden numbers and ratios were, including where the best place to put the backrest's axis of rotation is, and how far back people should be able to lean in those backrests. But the most important of what happened to me on that day is that I got to ask my live source how I could best improve my chair for quality of life and for ease of manufacturing. Remember that 3D printer we are currently in the process of getting? No? Good. Because I wish I didn't either. In about January of this year, Mr. Zimmerman, our tech implementation teacher, asked me about getting a 3D printer for the school. I immediately became incontinent with joy and found the perfect one immediately. It looks like this, and is the best thing we could ever hope for getting. Given that it is the best option out there and prints perfectly every time right out of the box. Naturally, I spent 30 hours making that happen as soon and as simply as possible. I succeeded in that we ordered it this year, and it will be here next year, which I guess is good enough. Whether or not you think it's just me taking all the sports boys and the tech squad on a joyride, The FVTC field trip has been the only culmination of my project that I have gotten to actually feel and interact with. During this field trip, I got to get final feedback on my product, use that feedback to introduce and help others with their similar interests in this area, and get to finally reap the benefits of what I have sowed. I think if I wasn't too busy being excited to share it with others, I probably would have cried during or on my way back from that trip. Being able to introduce others to the things I cherish and enjoy the most is probably one of the things I enjoy the most in life, and I'm so happy that I was able to do so. This project was special. For once in my life, I had too much information at my disposal. This book here, 1,000 Chairs, has enough content in it for somewhere from 500 to 1,500 notes. Between the chairs, their designs, and how they interact with and represent the design philosophies of their time, I'm holding 200 years of design in my hand right here. So naturally, I took as many small groups of averages to break that down into about 18 groups a year. For each of these ranges, I evaluated the ergonomics, manufacturing, materials, and design of each group. Considering that I've dragged on for the better part of half an hour already, I will share the highlights of each area. When the 1900s first hit, the ergonomics of that era somehow got worse. I don't know how, but they did. The chairs from this era went from sweeping forms to remarkably squarish and pyramid-shaped, to the point where you could use them as building blocks. Manufacturing was the most interesting in the 70s. This was because of a specific chair that came vacuum-packed in its sheath. Oh, this is getting close. I guess it likes me.
I can step on it here. There we go.
You should try to push it like that way, like this.
Try it. It's
I
got a
don't
good
know what-
angle.
I don't know what this
I
is.
did.
Okay.
The Up 6 chair was revolutionary in that it took up exactly the minimum amount of space possible and would have the minimum volume and weight until it reached the consumer. Once open, this package would inflate into a full-size chair, which you can see there. The most important development in materials was the advent of plastic in the 50s. Plastic is what made the contoured seat possible. Before plastic, you could only steam bend wood into a small variety of shapes, while steel was difficult and costly to form. The cheap and easily formed nature of plastic allowed contoured plastic to become a mainstay for seating that we now take for granted due to its prevalence. As far as the design aspect goes, the most interesting part for me is that in the 1920s, there was no furniture that matched the architectural style of the time. Sure, you had Art Deco buildings, but the furniture in the time no way at all resembled the way we consider the general aesthetic. Any and all implications otherwise were made more recently in the modern day as a sort of nostalgia or retroism. Thank you for politely bearing with me for the last half an hour. Do you have any questions about the things I was up until 3 o'clock writing about?
Good job, son.